Hey, everybody.
Hey, Professor.
How's it going?
Good, I guess. We got, yeah. How's your cat doing?
Oh, she's good. Yes, still old and hungry all the time, but she's doing fine.
Hey, Professor, I had a quick question about the project if you had time.
Sure. Yeah. What's up?
Just because I guess I you have to discretize it, right, with the n+1 for all the for
Yes.
FD for both of them, right?
Yep. Mm-hmm.
All right. And just wondering the scheme, so I have to do that and input the correct coefficients.
Right. Right. So the
Okay.
project mostly boils down to you have you're going to be using implicit Euler, and you're going to be using higher order convection schemes, and so. Um, I mean, first you should do it with kind of the basic schemes, which we have a lot of practice with. But once you kind of combine those two with with the few additional stuff that I have in there, that's basically the project.
Yeah, because I think I got the first one down. So for the finite volume,
Yep.
will you be providing that starter code, or is that?
Yes. Yeah. So actually, I just posted the starter code for the fine volume today, and so
All
I'm
right.
going to spend a bit of today talking about that because it's about that time. I think
All right.
timing is good. Where I think now that the midterm is done, I think now all the focus is going to be on the final project.
Yeah. So I
So
tried to knock out the first one, but now I was thinking about the second one. Okay.
second one, it's a little bit tricky, although it's actually easier than last year's finite volume starter code. So
All right.
so yeah, we'll talk about it a bit today.
Yeah, thanks.
Mm-hmm. Bring it up actually. Okay, I'll be right back. 1 minute. Yep. So if you're an undergraduate, you only have to use one. But if you are a grad student, in order to get or if you're taking this class for graduate credit, you have to do both. Yeah. But you can choose one or the other one. And after you see the starter code, you might. So I'm going to do it kind of the same way as I did last year. And so actually, after seeing the starter code, a lot of undergraduates actually changed and did the finite volume method. So we can take a look at that, and then you can decide what you want to do from there. All right, it's 5:30, so let's go ahead and get started. All right, good evening, everyone. How's everyone doing today? I just asked you guys 5 minutes ago because I was a little bit late, but I know you guys are doing good after the midterm, so that's a good thing, right? Good. Yep. So just like I promised, we have no more exams for this class, and so now it's just the final project, and so actually, there is one more homework assignment, and so the last two deliverables for this class are going to be that homework assignment and then the final project, right? So we're really winding down. So we have 3 more weeks to go, 6 more lecture sessions, and then the final project for that. So I know it's been a long and tough semester, and so basically every student that I've talked to this semester says, virtual learning has worn out its welcome quite a bit, and so to live your entire life in front of a computer screen and take classes, do homeworks, work on projects, all in front of the computer screen. Like I know it's tiring, and so just a little bit more to go, and then we can enjoy the summer a bit. Okay. So today the plan is we're going to continue our set of lecture notes on higher order schemes. Okay, and so this is kind of the last piece of the puzzle that you need for the final project, regardless of which method that you're choosing, whether you're doing a finite difference or finite volume. You're going to need to do higher order schemes, and so that's what we're going to do today. I haven't started looking at the exams yet. I've kind of been swamped with a lot of other stuff, mostly administrative, grad school, researchy kind of stuff. So last week was actually pretty bad for me, and so I am running a bit behind on my grading and stuff. So normally I like to finish grading the exams 1 week after you guys do it, and so my initial plan was to finish grading it by Wednesday. But with a lot of stuff that's kind of piling up, I might have to push that back until Friday of this week. And so my plan is to finish grading your guys' exams by Friday. Okay. And so I'll send an email out on that day, once I'm finished grading, just to let you guys know, how you guys did. But I've literally not clicked on it at all, just because there's just been a lot of other stuff going on. But by Friday, you guys should know. Okay. Okay. So I think that's all the announcements that I have. I don't have the next homework ready yet. So I think probably I'll wait until next week in order to post that, because a lot of it has to do with kind of the last set of lecture notes that we have, which is unsteady problems with finite volumes. And so we'll wait until then. And then, kind of overall schedule wise, I think we're still right on track. And so I think we should have time for about 2 or 3 lectures of open foam stuff. So hopefully that'll be exciting for you guys. Especially for those of you who want to use it for like personal projects or other school projects, that's kind of my plan for that. Okay. All right. Let's see. So are we starting a new set of lecture notes? It'll be the one, I think we started like maybe 15 minutes of it like last Monday. And so it's a continuation for that. And so it's lecture notes 12. Yeah. As long as I'm in a good mood when I do it. I try to be, yeah. So that's a big part of it. I want to make sure I'm in a good mood when I'm grading your exams. Will it be a short homework? It'll be about the same size as the rest of them. So it won't be any longer or any shorter than the rest of them. Yeah. Okay. So any other questions I can answer before we get started for today? Okay. All right. So let's go ahead and get started. And so today will kind of be a little bit of a hybrid. And so we'll be going over theory with the notes here, and then I'll be showing you some example codes that I've posted as well. Okay. Oh, actually, first thing. So I did promise before the class that I would show you guys the starter code for the finite volume version of the project, right? And so just to kind of remind you, so for the final project, you have if you're an undergraduate, you have the option of either doing the project with finite differences or finite volumes. But if you're a graduate student, you have no choice. You have to do both. Okay? So today I was working on the starter code for the finite volume. It ended up being a little bit trickier than I thought, mostly because of how the finite volumes handles the Neumann boundary conditions. But the starter code is posted, and I also posted what I call like an addendum to the final projects, because you have to modify things a little bit for the finite volume. So let me go ahead and share my screen. We can go ahead and take a look at that first thing. Okay. I think this is it. Yes. Okay. And so this is the starter code for the finite volume version of the project. Okay. So it starts out kind of the same up here. Okay. And so we have all the parameters for the project. So the length, the ends, left-hand side matrix, diffusion coefficients, stuff like all that stuff. So all this is the same for the finite difference. Okay. And so after that, then you jump into the time loop here. Okay. And you'll see that the format for this is basically exactly the same as the finite difference, where anywhere that you need to write code to complete the project, I've marked it with the section called to do. Okay. And so anything that has to do here can range anywhere from like just 1 line of code to maybe 6 or 7 lines. So I really tried to kind of break it down as much as I could for you. Okay. Okay. And so the way I've kind of organized this code is kind of the same as how I've organized the finite volume codes that we talked about last time, right? And so I've broken this up kind of integral by integral, because remember with finite volumes, we're really interested in computing kind of the 4 face integrals around your cells, right? And so we have the east integral, the south integral, the west integral, and the north integral. And that's where most of your code is going to be. And so I've broken that down in kind of the same way for you here, okay? And so, you know, a lot of this code will kind of make more sense as we go over the high order schemes. But one thing I'm going to do for you for the finite volume codes, because we have a little bit less runway, and we're kind of learning it in kind of real time and kind of applying it at the same time. I've already filled in one of these integrals here almost completely for you. And so if you look at the east integral here, you should see most of the or all of the coefficients here are already implemented for you. Okay, and so here you see we have the basic kind of central scheme. Okay, where you know, we assume basically kind of central differences in between the in between the different cells. And on top of that, I've also implemented what's called the quick scheme, which is what we're going to learn about today, which is the finite volume version of a higher order convection scheme. Okay, and so you can see here the coefficients are already fully implemented for you. And so all of this is fully done, and so you don't have to do anything for this. The only thing that you have to do here for the east integral is you have to implement the boundary conditions. And so basically, when the window opens, you know, then you're going to have to make it. You're going to have to write the code here. But the code here for that is you know, it's not that it's relatively simple. Okay, but I thought, you know, since we don't have that much runway with finite volumes, especially because we're learning unsteady stuff, kind of, you know, like a couple weeks before the project's due, I thought I would fill one in for you just to kind of serve as a reference, because the other ones are very similar to this. Okay. And so you can see if we move on to the south integral here, you know, there's a lot less filled in here. Okay. And so if you want to choose to do finite volumes, or if you're forced to do finite volumes for the final project, you can kind of use this as kind of a reference to fill in the code for the rest of the integrals here. So for the south one, the west one, and the north one. Okay. Okay. And so that's the starter code. And so that's posted today. And so the other thing that's posted is this thing, which I call the addendum. Okay. And so in order to have a result that that doesn't look crazy or doesn't look blown up, I had to make a few modifications to the code. And so mostly and there's 2 main changes. And so the first one is you have to change the velocity magnitude. And so if you look in the finite difference code, you know, I tell you to use a velocity magnitude of 35. And so for finite volumes, I want you guys to reduce that to 15. Okay. And then the second difference is how you handle the Neumann boundary conditions. And so, and this is just kind of a natural way of how finite volumes handles these a little bit differently than finite differences. Okay. And so make sure if you're going to do finite volumes for the final project, definitely read this addendum before you start. Right? And so all these files can be found on the course website. And so you go to files, and then you go to project. And so all of these guys are here, okay? And as well as a video that kind of shows you, what the solution will look like. So the solution looks different. So the video does look different for finite volumes, but it still looks reasonable, right? And so I wasn't able to get them to match exactly, but it still looks, it has all the essential qualities that I wanted it to have. Okay. All right, question. So will they still have those crazy exponents? No, it's not crazy exponents. It's just kind of minor changes to some of the magnitudes of certain things, just to make sure that the code ends up working out. Okay. Yeah. So it's very minor changes. Yeah. All right. Question. Any advice or recommendations you may have? I mean, I would say just if you haven't started it, I would definitely start it. Start very soon, because it's. I mean, in terms of lines of code, it's not that much, and so I think. In total, I'm having you guys write less than 100 lines of code. Yeah, I know it's it's what everyone says, but it's always impossible to predict what kinds of stumbling blocks that you'll run into until you start it. And so I'm always going to be here to help you out as much as I can. And the sooner that you start, the sooner that we can kind of discuss things and work through some of these issues. So and so I know it's kind of the boilerplate. It's the advice that everyone gives, but you won't know what issues you'll run into until you start. And kind of the sooner you start, the sooner you run into those issues, the sooner that you kind of come to me, then we can kind of work those through. Because if you can imagine, there's probably a lot of people are gonna wait, until maybe finals week to start this stuff, and during that time, I'm probably gonna be pretty swamped helping people, and so, the sooner that you start, now I'm a lot more free than I probably will be, leading up to the due date. So, yeah, start now. Run into issues, let me know, and then we can kind of work through them together. Yeah. Okay, so any questions on this before we jump back to the iPad? Okay. All right. So so all that's available to you, and then after the next couple set of lectures, you'll have everything that you need to do, basically everything for the project. Okay. Okay. All right. Now we're back on the iPad. Okay. And so the theme for today is going to be higher order convection schemes. Right. So kind of like what we were talking about a week ago, the convection term, which is remember the term that has to do with the active transport of our material through a velocity field. The convection term has a lot of problems, right? It's kind of the problem child of the family, where diffusion is kind of this really nice, proper child. Convection is kind of the unruly one. Okay. And so just to kind of summarize, some of the issues that we often have with convection is that oftentimes they can be unstable. Right? And so instability basically means that the solution can basically oscillate uncontrollably up and down, and so obviously that's not a good thing. Okay? And then something that was unique to when we had convection in 2D is we had this phenomenon called cross-stream diffusion. Okay. And so remember, cross-stream diffusion was this kind of artificial diffusion that appeared, because our convection velocity didn't align with our grid. Okay. And so both of these are problems. And so a lot of times the way that we solve these problems was we just simply refine the grid. Okay. But there's another way that we can kind of deal with these that doesn't involve refining our grid to some kind of crazy degree, and that's that's replacing the discretization scheme for the convection term with something that's better. Okay. And so let's start our discussion with finite differences, and then later on we'll talk about finite volumes. And so for finite differences, for FDM, if you remember, our convection derivative was basically just this first order derivative, just like that, right? So we had a d phi dx. Let's just start with 1d, and then we'll go from there. Okay. And so kind of the way that we discretize this was, we use basically a central difference scheme. Right. And the benefits of central difference scheme, or its characteristic, was that it was second order accurate. We had all those issues that we talked about before, but second order accuracy is usually pretty good. And so if you can achieve second order accuracy, then you're usually in a good place. Okay, but if we do better than this, so if we achieve a higher order of accuracy, then we can start to see some of these problems kind of go away. Okay, and so in particular, we're going to use a different scheme. Which doesn't have a formal name, and so we'll call it Central Difference Scheme 2, Electric Boogaloo. Okay. it really doesn't have a name, but it's still a central scheme that you'll see right there. But what you'll see is that it's even more accurate. Okay, and so what we'll achieve with this new central difference scheme is that we're going to achieve fourth order accuracy. Okay, and so that's 2 orders better than what we have, and that's going to actually solve a lot of our issues. Okay. All right. Any questions on this so far? Okay. Okay, and so why do I call it central difference scheme 2? Okay, so if we look at central scheme 1, right, we basically had a stencil that looked like this, right? Right. And so the stencil looked like, you know, we're obviously getting our derivative around our central node, which is node I, right? And then in order to compute the derivatives, we had to involve our 2 adjacent neighbors, since we had to involve our neighbor to the left and our neighbor to the right, or our backwards and our forwards neighbor. Okay. And so what we're going to do in central scheme 2 is that it's still going to be centralized. And so, you know, we're still going to have I in the center here, but we're going to add additional neighbors. Okay. Okay. Oh, I minus 2. And so you know what they say, you know, there's strength in numbers. And so the more people or the more nodes that you involve in this, the better scheme that you're going to have. Yep. Yep. The more the merrier. It's just like that. Okay. And so now instead of involving just I minus 1 or I plus 1, I minus 1, we're going to involve these kind of neighbors of neighbors terms. Okay. And so it's going to be, instead of having 2 terms in our stencil, we're now going to have 4. And so our central scheme 2 is given by the following. So we have d phi dx is equal to minus phi I plus 2 plus 8 phi I plus 1 minus 8 phi I minus 1 plus phi I minus 2. And all this is going to be divided by 12 delta x. Right? And so this term, or this discretization scheme right here, is a central difference scheme because, you know, we're balanced. And so you can see we have I plus 1, I minus 1, I plus 2, I minus 2. Okay. But because we're involving these extra terms, you know, what we see is that this scheme right here is fourth order accurate. And so how do I know it's fourth order accurate? Well, you can do the Taylor series expansion for this, and you can see that the first 3 error terms will go away. But I know Taylor's not really a popular guy around here, and so, you know, I'll spare you that. And so I'll say that, you know, you guys can trust me and say this is a fourth order accurate. Yes, it is a 12 delta x on the bottom. Mm-hmm. Yeah. Mm-hmm. Okay. And so you can see, you know, for this one, you know, we achieve a higher order accuracy, which is good, but we have to do a little bit more work because now instead of just doing 2 coefficients, now we have to do 4, which are, you know, all these kind of neighbors of terms. Okay. And so what I'm going to do next is I'm going to show you how this is implemented in a 2D case, right? So we're just going to kind of jump right to the right to kind of a complex case. I'll show you how to work this out by hand, and then I'll show you how it's implemented in code as well. Right, so any questions on this before we jump into that example? Whatever happened to McLaurin? Yeah, I'm not sure. I guess I'm not sure. I guess Taylor's series was I guess that's just kind of used more for kind of error estimating. But yeah, that's a good question. I guess Taylor was better at making friends with other people, which is always a good skill. Okay. All right, so let's go ahead and let's go. Taylor took over the hood. Let's go ahead. Let's go ahead and look at an example and see how this is implemented. All right, and so we're going to jump right into a 2D example. And so let's say that we have an equation that looks like this. And so for now, I'm going to do a steady case. And so, you know, part of your job for the final project is to, you know, take these higher order schemes and combine it together with the time marching scheme. And so And so I'm kind of leaving that out. I'm leaving that kind of out on purpose, so you guys can kind of work that out. But let's do a steady case just so you can kind of see how it works, right? So let's say we're going to have 10 partial phi partial x plus 75 partial phi partial y, okay, is equal to 3 partial squared phi partial x squared plus partial squared phi partial y squared. Okay. And so we have no source and no unsteady term. Okay. All right. And so we're going to work and we're going to solve this on the following domain, which for now it's not going to be relevant, but it'll be relevant when we do the when we go into code. Okay. Right. And so we're going to have phi is equal to 25 down here. Okay. Phi is equal to 25. Phi is equal to 50. And then phi is equal to 50 over here. Okay. Right, and so we have Lx, Ly, both of them equal to 1. Okay. And if we read off the parameters from the equation, we can see that u is going to be equal to 10. V is equal to 75. And then k is equal to 3. Okay. Okay. And so we're going to solve this equation with finite differences, but using a higher order scheme for the convection term. Okay. Okay. And so, the next exercise that we're going to do is we're going to start from the governing equation there, and I'm going to show you basically how to break it down into a finite difference equation. Okay. And so I know that these derivations are a little bit lengthy and they take a bit of time, but this is what you're going to have to do on the project, right? And so on the project, I'm not going to show you how to do a higher order scheme with a time marching scheme. Okay. And so I want you guys to kind of work that through yourself. And the process through which you kind of work through that, this is part of the process, right? So starting with the governing equation here, discretizing all the derivatives, actually writing out what all the coefficients look like this is part of what I want you to do for the project. Right? Okay, so let's go ahead and start with the equation, and let me do it in terms of just generic variables. And so just so that just so that you can kind of see what's going on here, right? And so I'm going to start with u partial phi partial x plus v partial phi partial y is equal to k partial squared phi partial x squared plus partial squared phi partial y squared. Okay. All right. And so what we're going to do at this point is we're going to take all these derivatives and replace them with a finite difference approximation using the higher order scheme for convection. Okay. All right. And so let me color code this just to make this a little bit easier. And so this first term I'm going to do in red. Okay. All right. And so for the first term we have u. Okay. And then we're going to use a higher order scheme for this. Okay. And so we're going to copy basically the same scheme that we had on this page, but we're going to apply it for this equation. Okay. All right. Okay. And so the higher order scheme is going to be minus phi I plus 2 comma j. Okay. And so remember we're in 2D now, and so we have to do both the I and the j. Okay. Right. Plus 8 phi I plus 1 comma j minus 8 phi I minus 1 comma j plus phi I minus 2 comma j. Okay. And of course, all of this is divided by 12 delta x. Okay. All right, and so that's the first convection term. And so, from here, I'm going to do the next ones, but on the next page, just because they don't fit here. All right, so just let me go ahead and establish the colors for now, just so, we don't have to keep flipping back and forth. Okay. All right, and so after we've replaced the other derivatives with their finite difference approximations, we're just going to organize everything into the respective coefficients. Okay. All right, any questions on this so far? Okay. All right, so let's do the y convection derivative. Okay. All right, so that term's going to be v. Okay. And we're going to do the same thing, except now we're going to apply the differencing on j. Okay. So we're going to have minus v I j plus 2, okay, plus 8 v I j plus 1 minus 8 k is equal to 3. Yes. Minus 8 phi I j minus 1 plus phi I j minus 2, okay, all divided by 12 delta y, okay. Right, and so that's the convection terms, and so now we have the diffusion ones, and so these are exactly the same as we've seen before. So I'm just going to write these down pretty quickly. Okay. Okay. Can I fit this in? Let's see. Phi I j plus 1 minus 2 phi I comma j plus phi I j minus 1, kind of. Okay. And so, that's all of our terms there. Okay, so that's all the finite difference approximations. And so now all we have to do here is just reorganize all the coefficients. Okay. Yes, yeah. So the diffusion, we're not going to do anything different with the diffusion term because the diffusion term doesn't have any problems, and so it's like the nice child, and so it's the one that does nothing wrong and is always perfect. And as the parent, we said, yes, we know and we love you, and we changed nothing about you. But the convection term, that guy needs to kind of shape up his act. That's why we changed him. Yeah. Okay. And so we're going to reorganize these into coefficients. And just like we always do, we're going to assume the grid spacing is the same. Okay. Which is going to be delta. Okay. And then we're going to multiply this entire equation by delta squared just to get the delta out of the denominator. Okay, and so we do that. We end up with the following expression. Was I a convection child? Yes, I am. I am the convection child. Okay, and so we multiply everything by delta squared, and we reorganize everything, and we end up with the following. And so we have a lot more terms here. So usually, remember, usually we only have coefficients for my ID, left ID, right ID. And then up ID, down ID, but now we have left 2, right 2, up 2, down 2, and so it's a lot, and so it's kind of crowded now. Okay. All right, so first we have u delta minus u delta divided by 12, and this is the coefficient for phi I plus 2, comma j, okay, plus 2 delta u divided by 3 minus k. And this is phi I plus 1, comma j, okay, plus minus 2/3 delta u minus k. This is the coefficient for phi I minus 1, comma j, right? Plus u delta divided by 12, phi I minus 2, comma j, okay? Plus minus v delta divided by 12, phi I j plus 2, okay? Plus 2/3 delta v minus k, phi I j plus 1, okay? Then we have minus 2/3 delta v minus k, phi I j minus 1, okay? Plus v delta divided by 12, phi I j minus 2, okay? Plus 4k phi I comma j, okay? And all this is equal to 0. Right, so it's a lot of organizing and a lot of places, where, you can get kind of lost. And so, definitely, I went through this really quickly now, but, when you're doing this for your projects and you're deriving these coefficients, definitely take your time, because a sign error here or an arithmetic error here can really just throw a wrench into everything. So, take your time and make sure that all of when you're reorganizing the terms, make sure everything matches up well. Okay. Okay. So any questions on this so far? I know you guys are probably still copying it down, so I'll hang out here for a little bit. For the I j minus 1 term, it should be a plus. So they're all pluses. Yes. Mm-hmm. Right. So I guess while you guys are still kind of copying this down, I'll go ahead and kind of say that this scheme here is good, and so it's better than our usual scheme, but we have a little bit of a stricter requirement here that we didn't see from before, right? Because remember, the issue that we had with finite differences before was that in order to apply our finite difference equation, we had to have all of the neighbors available to us, right? And so in order to apply our old one, we had to have a neighbor to the left, we'd have a neighbor to the right. It's your left and my right, your left and your right, okay? A neighbor above us and a neighbor below us, right? And so if we didn't, then we ran into some issues, because then we had to apply a boundary condition, okay? Here, the situation is a little bit more complicated, because in order to apply this this scheme right here, not only do we have to have our immediate neighbors, but we also have to have neighbors of neighbors too, right? And so in order to use this equation, we have to have a node, two steps in each direction in order to apply this, right? As you can imagine, this is a little bit of a stricter requirement. And so for some nodes, for this scheme, it's very possible that we have some nodes that aren't on a boundary, but that aren't on a boundary, but we still can't apply this method because we just don't have enough neighbors in a certain direction. Okay, and so what you need to do is you need to kind of say that we can use this for all the interior nodes, but there's going to be a thin layer of nodes kind of on the exterior of the domain that's not quite on the boundary, where we have to kind of go back to what we did before. Okay, and so let me go ahead and draw and illustrate what this kind of means. Okay? All right, so is everyone done copying this thing down? Okay, so I'll take that as a yes. Okay. Okay, so let's say that we have our 2D domain here, and so this is overall, okay, and we know that for all the nodes that are on the boundary, for those nodes, we're going to apply our boundary conditions. And so none of that changes. And so that's going to be exactly the same as we did before. Okay. But what's going to be new here is that if we look just one layer on the inside, and so we just peel one layer off the onion, okay, and we look at kind of this interior shell of nodes right here. Okay. And so technically these orange nodes are interior nodes. But the issue with these orange nodes here is that there's not enough neighbors to apply the higher order convection scheme. Okay. And so if we look at just kind of this example right here that I'm drawing with the dots, right? And so if we look at this node right here that I've circled, right? It might have neighbors, 2 neighbors above it, 2 neighbors below it, 2 neighbors to the left. But if we're going to the right, we only have one. We only have one neighbor in that direction. And so if we try to apply our high order scheme, right, we're going to be looking for a neighbor over here. But this guy doesn't exist. Okay. And so if we try to apply our high order scheme here, you're going to get a MATLAB error, because you're referencing a node that just doesn't exist. Okay? And so for this, for these orange nodes, which are kind of just one layer on the inside, what you have to do here is you have to go back and apply kind of our basic central difference scheme to these ones. Okay. But only for that layer. Yeah. And so, in the worst case, you're going to get index out of range. Actually, that might be the best case because then MATLAB tells you there's an issue. But in the worst case, you might be adding coefficients on lines that that you don't want to as well. And so that's even worse because then you have an error in your code, but then it's like a conceptual error. So MATLAB's not going to catch it, and you're just going to be running your code and wondering what the hell is going on. Okay. And so if we peel one more layer off the onion, then we have all of these interior nodes, which I'm going to shade in. Okay. Right. And so for all the nodes in the red right here, we're going to have enough neighbors to apply the higher order scheme. And so that's exactly what we're going to do. And so you have to be careful about this when you're applying higher order schemes. And so, next, what I'm going to show you is I'm going to show you the MATLAB code, from which you can account for this. Okay. All right. Any questions on this before we jump into the MATLAB example? Okay. So let me go ahead and hop back on my laptop. Okay. And this is the code that I want you to look at. And so this code is posted on Canvas, okay? And so if you go onto Canvas, let's see, let me go to home, you go to week 14, okay? And so this code is downloaded from this link right here. And so there's a link that says higher order FDM example. And so that's exactly the code that I'm gonna show you right here, okay? So back to the code, okay. And so this here is an example of how you implement a higher order convection scheme for finite differences. Okay, so this is the exact same problem that we were looking at before. So you can see that the x velocity is 10, the y velocity is 75, the k is 3, okay? And then what we're going to do is we're going to implement the coefficients that we saw, okay? All right, so first thing, and so, first thing to see, so, for the last few weeks, we've kind of been glazing over this section of code, because remember, this is the part of the code where we compute the ID numbers, okay? But, because we have to summon the power of our farther neighbors, we have to add some code to this to compute those neighbors of neighbors, okay? And so I've labeled that section of code here to obtain the ID numbers for all of the distant neighbors, okay? Right, and so I'm going to give them names left ID2, right ID2, up ID2, and down ID2, just to indicate that these are the ID numbers from 2 away from us, okay? All right, and so from here, I just to kind of make the code a little bit easier to parse, what I've done is I've broken up the coefficient contributions, where I do the diffusion terms, and so remember the diffusion doesn't change at all, okay? And so for the diffusion terms, we have a positive 4k for the diagonal term, okay? And so this plus this a my ID plus 4k, and so that corresponds to this phi ij coefficient right here, okay? Yes, yeah, so the double lines is or, yes, yeah, so we'll go over that in a bit. Yeah. Okay, and then for all the immediate neighbors, remember the diffusion term doesn't have any higher order neighbors, right? So the diffusion term is just good with just its 2 pals just right next to it, or I guess in this case, the 4 pals right next to it, okay? As you can see, all those diffusion contributions are just going to be a minus k. And so we have a minus k on the right neighbor, we have a minus k on the left neighbor, we have a minus k on the up neighbor, and we have a minus k on the down neighbor, okay? And so those are just neighbor ones. And so, then we just use left ID, right ID, up ID, down ID, without left ID 2, right ID 2, up ID 2, stuff like that. Okay. All right, and so now let's jump into the section of code that does the higher order schemes. Okay, and so I've broken this down into 2 directions. And so first I have the x direction, and then I have the y direction. And so let's do the x direction first. Okay, and so for the x direction, first thing I'm going to check is I'm going to check to see if we don't have enough neighbors to implement the higher order scheme, okay? And so that's exactly what this checks. And so if you read the comment here, you can see that for this comment, it says that not enough x neighbors to do higher order scheme for the x convection derivative, okay? And so that occurs when I is equal to 2. And so that tells us, when we're basically not on the very left edge, but one inside of that. And so that vertical edge right there is when I is equal to 2, okay? And the other time when we don't have enough x neighbors to do the higher order scheme, we do, that's when I is equal to nx minus 1, okay? Because if I is equal to nx, that puts us on the very right border of the domain. And so one layer of the onion right on the interior, that's going to be nx minus 1, okay? Right. And so if we're in these cases right here, then we can't apply our higher order scheme. And so we just use our basic central difference. So basic central difference is going to be u times dx times 0.5, which is the same thing as divide by 2. So let me go ahead and replace this, divide by 2. Okay. Right. Right. Question? Let me see. Okay, and so that's the special case, when we don't have enough neighbors. But when we do have enough neighbors, you can see that I've implemented the coefficients here. Okay, and so when we do have enough neighbors, we can implement all of these coefficients here, right? And so if we look at the neighbor that's immediately to the right, and so this is going to be a at my ID right ID. Okay, you can see here that we have a positive 2/3 u times delta. Okay, and so you can see I have 2 times x velocity, which is u, times dx, which is delta, divided by 3, okay? And so for the immediate left neighbor, we have a coefficient of minus 2/3 delta times u, okay? And you can see that right here. And so let's look at the right 2 and the left 2 neighbors, okay? And so for the right 2 neighbor, you can see here we have a negative u delta divided by 12, okay? So you can see I have that coefficient right here, okay? And I've left the comments here to show you, which phi term that this is a coefficient of. And then for I minus 2 comma j, you can see we have a positive u delta divided by 12. Okay, and so that's what this guy is right here. Okay. All right. and so, you know, the actual implementation of the coefficients is not difficult. I think the most difficult part of using the higher order scheme is kind of this extra case that you have here for just checking if you have enough neighbors. Okay. Right, and then the same thing, and then basically the code kind of repeats itself for the y directions. And so, you know, you check if you see if we want to check to see if we have enough neighbors above and below us. And so if we don't, then we use our basic central difference scheme. But if we do, then we use our higher order scheme that we have, you know, over here on the left. Okay. Right. All right. So any reason do I define u and v as x velocity and y velocity, not just u and v? Yeah, I flip flop, and so sometimes I use u and v, sometimes I use x velocity and y velocity. You know, kind of my thought process for that is x velocity and y velocity are a little bit more descriptive than u and v, because u and v can be anything, so they're just single letters, right? And so if I say x velocity, y velocity, that's a little bit more descriptive. And so when you're looking through your code later, you can say that, you know, this x val right here, that's going to be the x velocity. But if I had just changed this to u, you know, I mean, u corresponds to the same symbol as the notes, but, you know, u could also mean a bajillion different things, right? And so, you know, I try to be a little, I usually try to be a little bit more descriptive with my variable names, but sometimes I get lazy and sometimes I use u and v. Yeah. Yeah, but you can define u and v with the comment. Yes, you can do that too. But yeah, so I know I'm not the most consistent person with that, but usually the better thing to do is to use kind of more descriptive variable names like this. And so what else would u and v be in these codes? You know, for these codes, you know, kind of relatively speaking, you know, these codes that we're writing for this class have a very narrow scope. But if you're talking about kind of a much bigger code base, like say that you're contributing to an open source project, or, you know, you're writing like a multi-physics kind of solver, you know, u and v can mean a lot of different things in those codes too. And those are codes that are, you know, literally tens of thousands, hundreds of thousands of lines long. And so, you know, for those codes, it really pays to have, you know, really descriptive variable names. Because a lot of times it's not only going to be you that's reading this code, it's going to be, you know, other people that's going to be using it as well. And so, you know, for their sanity, it helps you use descriptive variable names. I remember the first code that I worked with in grad school did not follow these conventions, and it was a code that was about 150,000 lines of Fortran code that literally used variable names like G, G2, G3, G4, and they aren't even related to each other. They all mean very different things. And so I'm like, why are you using G for all these things? And it was a nightmare. I almost quit grad school because of that code, but. And so that's why I you know, I really recommend you guys to use, you know, descriptive variable names. I get it, you know, sometimes, you know, I'm lazy too, but it really helps in the long run to use kind of more descriptive names. Yeah. It was actually, no, it wasn't. So this was a code that was started in the 70s. And then people just kept adding to it, and then no one wanted to convert it to C and C++ because it was 150,000 lines, and so it just stayed as Fortran. Yeah. Okay, so any questions on this? So this code's available for you guys, and so it's so you can download this from the Canvas site, and you know, you can take a look at that. So it was 150,000. Yes. All right. So any questions on this before we start talking about the quick scheme? Okay. All right. So let me go back to the iPad. Okay. And so that's higher order schemes for finite differences. And so there's you know, there's not much to say. And so, you know, I think it kind of builds a lot on what we've learned up to this point. Okay, it's more just kind of implementing it and checking to make sure that you have enough neighbors, right? And so the higher order scheme for finite volumes, there's a little bit more involved to it, but you know, it's not that much more. And so, you know, we're going to put the finite difference hat down, and we're going to put our finite volumes hats back on because we're going to need a lot of that kind of background information. Oops, we're still red. Okay. All right. And so now we're gonna see how we implement the higher order scheme for finite volumes. Okay. And so just like we did for finite differences, I'm gonna skip kind of straight to 2D, just because that's going to be the most applicable for your project. Okay. And so kind of recall for finite volumes. Remember, the focus for finite volumes is to evaluate each of the 4 face integrals. Okay. Okay. And so I'm just going to do one example here. And so let's say that we have the integral on the east face. Okay. Okay. You'll see what we have for the expanded one. We're not going to go diagonal though, so don't worry about that. Okay, and so for the east integral, remember we had this, so we had phi times the velocity dot product with n minus k gradient of phi dot product with n, okay, ds, right? And then after applying our integration rules here, we end up with the following expression. Okay? As we have phi a little e u minus k partial derivative of phi with respect to x on the east face, okay, times technically times delta x, but we'll ignore that for now. Okay. All right. So just like before, just like with finite differences, our diffusion term is perfect, so we don't have to do anything for it, and so we can just do the same thing as we always do for this. Okay. And so that term doesn't have to change. We can do whatever we want. And so the focus is going to be, how do we estimate this? Okay. All right. And so this phi sub little e. Okay. I remember I gave it a lowercase e on purpose because remember, this is the solution value on the east face. Okay. And so it's not a centroid cell, right? Or it's not a centroid phi value. Okay. And so the way that we approximated this, right, is because the east face sits right in between phi sub c and phi sub big E. Okay. What we did for this before was we just simply took an average in between the two things that it sits between. Yes. Yes, multiplied by. Oh, I guess technically it's delta y because it's a vertical integral, but it's multiplied by delta. Yeah. Mm-hmm. Oh yeah. It's not an exponent. It's just a multiplication. Yeah. Sorry about that. Let me go ahead and fill that in. And so here we have delta y. Yeah. Yeah. It's just straight multiplying. It's not an exponent. Okay. Okay. And so what we've done before was we said that phi sub little e is equal to phi sub c plus phi sub big E divided by 2. Okay. And this right here, this was kind of our basic central scheme. Okay. And so this was kind of the thing that intuitively kind of made the most sense for us at the time, was just simply just take an average of this. Okay. All right. And so what we'll do now is, instead of using this, this kind of central scheme, which, if you recall, remember is basically it sets a linear function between the two. We're going to make this higher order. Okay. And unlike the finite difference version, this one actually has a real name. And so it's not just central scheme 2 electric boogaloo. This one actually has a name. And so, that's kind of the nice thing about it. Okay. Okay. So any questions on this? Okay. All right. So let me draw visually what's going on with this guy. Okay. And so if we have 2 cells here. Okay. This is where phi sub little e would be. Okay. And this is where phi sub c and phi sub big E are, right in the middle of the cells. And then, what we did in the previous one was we basically said if phi sub c was right here and phi sub big E was right here, okay? If we just kind of plotted their values kind of against each other, okay? And then the value that we had on the previous page basically assumes that we draw a straight linear line. And then phi sub little e is here just right in the middle. Okay. Right. And so, I think someone asked a question, a few weeks ago about, is linear kind of the only option for this? And so that was kind of foreshadowing to what we're going to do now, because instead of a linear line, what we're going to use now is a quadratic line. Okay. And so we're kind of moving up. We're moving up in the world a little bit. Okay. So we're moving on from linear functions and then using quadratic ones now. Okay. And so that sounds great. But the only problem with the quadratic line is that instead of if you kind of think about a quadratic function, right, in order to specify a unique quadratic line, we need 3 points instead of 2. Okay. And so what this basically means is that we're going to have to implicate more neighbors into our scheme. Okay, so we can't just use phi sub c and phi sub big E, and so we need to implicate one more neighbor into this. Okay. It's not that I forgot the talk. I mean, this was coming no matter what. And so, if anything, you kind of predicted where the class was going to go. Okay. Okay. And so this is going to give us our quick scheme. And so quick does not mean that it's fast. Actually, it's kind of the opposite. And so it kind of takes a bit more time, but it's actually an acronym. Okay. Right, and so the acronym stands for this, and so it stands for quadratic, upwind, interpolation, okay. There's a word here that's not in the acronym just because it would make it a crappy acronym, okay. And so there's 4. And so it's quadratic, upwind interpolation for convective kinematics. and hence we have quick if we ignore the 4, okay, which we typically do for acronyms. Okay, and so what you'll see is that we're actually gonna have 2 different options here for the quick scheme, because we know that we have to implicate one more neighbor, right? Because we have to have a 3-point quadratic, right? But we have an option here, so we can either pick one neighbor to the right, or we can pick one neighbor to the left. Okay, and both actually see the same amount of action, and it really depends on the physics. Okay, and so I'm going to show you basically 2 versions of the quick scheme, and I'll show you basically when you would use one version over the other. Okay. All right. So any questions on this before we move on? Yes, and there's still no diagonal stuff. Yeah. It's just going to be one more on the left or one more on the right. Okay. All right. So let's do an example for the case where we want to approximate phi sub little e. Okay, and so let's do version 1 first. This doesn't imply that it's first or better or anything like that. It's just the one that I just ended up drawing first on the notes. Okay. And so this is the case where we're going to implicate one more neighbor to the right. Okay. And so we're going to call that rightmost neighbor phi sub 2e. Okay, so that's saying that we move east 2 spaces. And remember the phi value that we want to approximate sits right here. Okay. All right. And so under version 1, we're going to basically draw a quadratic function that goes through these guys. Okay. And so I'm not going to go through the derivation for these. I'm just going to give you the final results, and the final result has the following coefficients. And so basically under the quick scheme, phi sub little e here is going to be 3/8 phi sub c plus 3/4 phi sub e minus 1/8 phi sub 2e. Okay. Right. So that's version 1. Okay. And then now let's go over version 2. Okay. In version 2, we're going to implicate one neighbor to the left. Okay. And one neighbor to the left, of course, that's going to be phi sub w. Okay. And so now we have this trio here of phi sub w, phi sub e, and phi sub c. Okay. And then just like before, the phi value that we're trying to estimate here is between phi sub c and phi sub e. And so that's right here. Okay. So we have phi sub little e. And so under version 2, we have phi sub little e is equal to minus 1/8 phi sub w plus 3/4 phi sub c plus 3/8 phi sub e. Okay. And so if you compare version 1 and version 2, they're the same coefficients. So we have a minus 1/8, we have a 3/4 and a 3/8. They're just kind of shifted around depending on which version that we want. Okay. 3/8 is kind of telling you of Simpson's rule. It's similar. I mean, Simpson's rule assumes a quadratic function, and so it's that's why you see that 3/8 there. Yeah. Mm-hmm. Yep. That's not a coincidence. That's for sure. Okay. And so we have these two versions of the of the quick scheme. Okay. And so now the question is, how do we choose which one over the other one? All right. And so to help us choose, let me go ahead and return back to what the acronym stands for quick. Okay. And remember, and I want to focus on U. Okay? And so the U in quick scheme stands for upwind, right? And remember, what upwind basically says. And so what upwind basically means is that, we want to place more weight on the streams that are on the nodes that are upstream, or the cells that are upstream of the convection velocity. Okay. Because remember, throughout this, we're doing this for convective term, right? And so the convective velocity, can either go this way if it's positive, okay, or it can go from right to left and go this way, right? And so, as you can probably imagine at this point, the quick scheme that we choose is going to depend on the direction of the convection velocity. All right. And so let's look at version 1 first then, okay? So in version 1, you can see that we placed one more neighbor to the right, okay? And so what this tells us is that, this will work really well if the velocity is going from right to left. It works well when it goes from right to left because we're placing more emphasis or more weight on those cells on the right. Okay, and so you want to use version 1 right here when the velocity is negative, right? And so if the velocity is negative, that means it's going to the left and it's going from right to left. Right? And so conversely, we want to use version 2 here when the opposite is true. And so in version 2, since we're putting one more neighbor on the left, that's going to work really well when our velocity is also coming from the left. And if our velocity is coming from the left, that means our velocity is positive. So it's going to look just like that. Okay. And so this you want to use for positive velocity. Okay. So depending on which direction your velocity is, that's what's going to determine which quick scheme that you end up using. All right. So any questions on this? Okay. All right. And so that's the quick scheme. But I've only done the quick scheme here for the east face. Oh, version 2. Yeah, I definitely can. So version 2, we've included one more neighbor on the left. And so in order to make our scheme upwinding, we want to use this scheme here when our velocity goes from left to right. And so that's going to happen when our velocity is positive. All right. And so, I've only shown you how to do this for the east face integral. And so as you can imagine, if you want to apply this for the entire finite volume method, you have to come up with similar expressions for the north integral, the west integral, and the south integral as well. Okay. And so in this next example here, I'm going to show you how I work it through by hand, which will probably just kind of start today, and then we'll finish up on Wednesday. Okay. And so for this example, I'll work through, each of the different integrals, and I'll show you where you would use one over the other one. Okay. All right, and so for this example, let's say that we're working with the same problem as before. Okay. And so it's a steady problem with a u convection velocity, v, k, and all that stuff. Okay. But this time we're going to use our convection scheme or quick scheme with finite volumes. Okay. Okay. And so, the way I'm going to do this, I'm going to break down each of the 4 different integrals, and I'll show you kind of the 2 cases that we have to do depending on the direction of the velocity. Okay. And so for this example, I know that, u is equal to, I think, 10, right? Yeah, u is 10, and v is 25 or 75. Okay. And so, we don't have to write, in this case, because the velocities are constant, we don't have to write out every single one. But just for kind of demonstration's sake, I'll show you how I wrote down every single one, and then I'll show you how we kind of pick one based on the direction of the velocity. All right, and so let's start with the one that we just did from prior to this, and so let's do the east face. Okay. And so for the east integral, we have 2 different versions here. Okay. And I'm going to include the diffusion term in this as well, even though that's going to be the same as it always is. Okay. And so let's do version 1 first. Okay. Okay. And so under version 1, we have this expression here. Okay. And remember, we want to use this when u is greater than 0, right? And so that's when u is positive. And then our other choice here is going to be u 3/8 or minus 1/8, sorry, minus 1/8 phi sub w plus 3/4 phi sub c plus 3/8 phi sub e. Okay. Right. Minus k phi sub e minus phi sub c over delta x. Okay. And we want to use this one when u is less than 0, and it's going from right to left. Okay. Right. And so in this case, since our velocity is positive, right? Since our velocity is 10, and so we know it's going from left to right, then the quick scheme that we use for this, just for this problem, is going to be version 1, because that's going to place more emphasis on the oh, I'm sorry. What am I doing? We want to use version 2. And I got these all mixed up too. I'm getting confused. All right, so we want to do this when u is less than 0, and we want to do version 2 when u is greater than 0. Sorry about that. Brain fart. And so in this case, because u is a positive 10, we want to use version 2 because that's going to place more weight on the left side. Okay. All right. So any final questions on this before we wrap up for today? Okay. All All right, so on Wednesday, we'll pick up this example. I'll show you the north, the west, and the south integrals, and again, how you choose which one based on the velocity, right? All right, so thank you guys. Thank you guys for tuning in today. Have a great evening, and I'll see you guys on Wednesday.
Thank you, Professor.
Thanks, guys.
Professor.
Yep. Mm-hmm.
So when I was asking earlier about version 2, was basically where do you get like the coefficients from?
Yeah, it's a good question. And so the way you get the coefficients is that you actually draw like a quadratic function in between these guys. And so, you would draw like a function that looks like that. And then you basically optimize it so that, you basically try to make sure that the quadratic function passes through each of the phi values. And so I skipped over that just because it's, I just want to focus on the implementation, but that's what you would do for both, version 1 and version 2. Yeah, so the derivation is the same for those ones. It's just that you use different different points for them. Yeah.
Oh, okay. So we just basically just use your formulas.
Yeah, exactly.
Don't try to derive them. Basically, what you try to say.
Yeah. So we're not gonna have time to derive them here, but that's how you do it. Yeah. If you notice, each of the two versions have the same members, and so you can see there's a -1/8 and -1/8. There is a 3/4, and so there's a 3/8 as well. As you can see that they come from the exact same function. It's just that one is shifted to the right and one is shifted to the left.
Yeah. All right. Thank you, Professor.
Yep, no problem. Sean, did you have any more questions? Okay, all right. So if there's no more questions, I'm going to go ahead and sign off. And so I'll see you guys on Wednesday.